Alright, so we are in geometry. Today's date is Thursday, October 17th. We are talking about the winter benchmark practice. So this is geometry and congruence. This is going to be for our CASP. I think we should be able to do this tomorrow. Make sure that your packet is done. This is going to be worth 100 points in the homework category. So let's go ahead and get started. Number one, oh, and by the way, if you don't finish this packet, you need to finish it for homework. So, number one, which pair of transformations is the same as a reflection across the y-axis? All right, so a reflection across the y-axis, what does that even look like? So if I come back to here, let's assume that we have some shape. If I reflect across the y-axis, what is that going to look like? So let's reflect this shape across the y-axis. That's the shape that we should be getting. So we can all see that that is a reflection over the y-axis. Let's try the first one, a rotation of 90 degrees counterclockwise and then a reflection across the x-axis. Properties so that it goes. I have an idea, so let's go ahead and delete this guy. If we rotate this triangle around this point clockwise by a degrees, and I get rid of these other gross points. Actually, we don't need any of these points. Points go away. So if I rotate now by 90 degrees, it's going to end up down there. I don't know why the point's still showing. It comes down here 90 degrees, and then a reflection across the y-axis. A reflection across the y-axis is going to end up over here. You can see that just by reflecting this about the y-axis is going to end over here. Again, we want to have something that ends up right there. Alright, so far that did not work. So it's not B, a rotation of 180 degrees and a reflection across the x-axis. So what's going to happen there? So if I rotate it 180 degrees, it's going to end up there, and then I'm going to reflect it over the x-axis. Hey, check that out. That was the reflection over the y-axis. Again, a reflection over the y-axis looks like this. So if I reflect this over the y-axis, it's the same thing. So the correct answer over here is indeed C, and let's see why D is not correct. A rotation of 180 and then a reflection across the y-axis. So, oops. So if I do 180 degrees and then reflect it over the y-axis, that's going to end up in the fourth quadrant over here. It's going to end up right there. So that one's not correct. For problem number 2, we have to use the diagram and we have to make a proof. We haven't talked about proofs that much yet, but I have given you an informal proof of this. Why are the sum of interior angles of a triangle must be 180 degrees? We've seen this diagram before. It should look familiar, and the correct answer is the same proof that I gave you guys using alternate interior angles, and then adding all three of these up. But let's see what the choices are saying. It's saying that angle 4 and angle 2 are congruent. Angle 4 and angle 2 are congruent. I mean, just right away, they don't even look congruent, and they're saying alternate interior angles. No, alternate interior angles would have been 4 and 1 and, no, 4 and 2 and 3. Those would be alternate interiors if I added 2 and 3 and 4. So A is not correct. It's not even close. Let's see B. 5 is equal, or 5 is congruent to 1. That's correct by alternate interior angles. 6 and 3, alternate interior. That one looks good. So we'll come back. That one might be true. 1 and 2 and 3 are all 60. 1 and 2 and 3 are all 60. How'd they get that? You can't just assume they're 60. What if this angle is like this? Or we don't know. Yeah, you can't just assume. That's assuming it's definitely not C. D is saying 7 and 3 equal 180. Yeah, they do equal 180 if I add those two. We haven't talked about it, but those are called same side interior angles, so they always add up to 180 degrees. That is true. Those are both true. 7 and 6 add up to 180. Well, that also is true. 7 and 6 add up to 180 because it's a straight line. They're called supplementary angles. So first line good, second line good, and then no, bad. How did they? Okay, so if they're talking about measure of angle 2 here, they have to somehow mention measure of angle 2. Have they ever mentioned measure of angle 2? No, they have not. So their chain of logic is flawed. I mean, just by default, it's B. Let's take an in-depth look. So we have alternate interior angles saying U2 are equal, and then U2 are equal, or I guess congruent, and then 1, 2, and 3 add up to 180. Well, yeah, that's true. It's a straight line. Those are supplementary. And then 5, 2, and 6 equals 180. That's exactly the chain of logic that we used in our class. So the correct answer is B. For number 3, Ron is claiming that the opposite sides of a quadrilateral are always congruent. So just to give you an idea of what's going on here, so he's saying if I have, I don't know, a rectangle, any quadrilateral really, it's saying that this side and this side are always the same length. They're always congruent. So we need to disprove him, and we just have to make sure that we're a quadrilateral. So all 4 of these are quadrilaterals. We've talked about them all before. Which one of these would show that he's false? So we have to disprove him. A non-square rectangle, I just drew that. A non-square rectangle, if I drew it correctly, it would look a little bit better. Looks like that. Well, those 2 sides are congruent. Those 2 sides are congruent. So that matches what Ron is saying. We're trying to disprove him, so no. A parallelogram, what does that look like? A parallelogram looks like this. Again, these sides are congruent. These sides are congruent. Not helping us. No. That still matches Ron. A rhombus. So again, a rhombus is like a square that got sat on by an elephant. So we have a square, and it's still a parallelogram. A parallelogram could be something that looks like this, though. As long as they're parallel sides, right, and slightly squished. So rhombus, all of these are equal, and still this is equal to this. They're both congruent. These are both congruent, not helping us at all, rhombus. You are good for nothing. Ooh, a trapezoid, that's going to be the answer. So a trapezoid looks like this. This length and this length are definitely not congruent. I mean, look, that one's tiny, that one's big. They're definitely not the same. So D, the trapezoid, that is going to be how we disprove Ron. You're wrong, Ron. All right, so for number 4, Jessie's drawing a triangle ABC, and she says that AB has a slope of 3/4. So it looks like we're not using anything else. So just ignore everything else. Let's look at AB. So assume we have some line segment that's 3/4. And she's going to do the following things, and she says, yeah, I'm still going to have the slope of 3/4 after doing these things. Let's see if she's true or not. So you're going to have to do these in your mind for the actual test, or the benchmark test, I should say. But I have technology so I can help you visualize what it's going to look like. So let's assume that we have, I don't know, some AB. It has 3/4. So 1, 2, 3, 4 in the x direction, 1, 2, 3 in the y direction. That means I have a slope of 3/4. And again, if you ever forget that, let me come back over here. I can write that down. You should know the definition of slope. Slope is your change in y divided by the change in x. And if I come back to this diagram, you can see that yes, the change in x was 4, the change in y was 3, so I do indeed have a slope of 3/4. So from here, let's go ahead and apply the transformations. So 180 degrees around the origin. So let's twist this guy around, and yeah, it looks like it's the same slope, just eyeballing it, and 1, 2, 3, 4 in the x, 1, 2, 3 in the y. Yeah, that's good. Good job, Jesse. I didn't even guess that one. That's pretty good. Reflection across y equals 2. I'm going to guess this one is not going to work. So if I have y equals 2, and I want to reflect it, so let's get rid of that line segment down there. If I want to reflect over this line, so let's go ahead and say, let's reflect this segment over this line. Oh, no, sorry, Jesse, you're incorrect here. It was a positive slope. This is clearly a negative slope. It's now a negative 3/4, so no, you're wrong. Translation up 1.25 units. Well, if I'm just moving it up, the slope should stay the same, but let's go ahead and check it out. So if I have this segment, and I want to go up, so it's going up this amount, 1.25. We'll see the same. If I'm going to translate this segment by this vector, There it is. It's the same vector, basically, or it's the same slope. We're good. Yeah, that one makes sense. I'm just moving it up. A reflection across the x-axis. I don't think this is going to work. Let's go ahead and see what happens here. So a reflection across the x-axis means I'm going to go here and reflect this point on the x-axis. Yeah, that makes sense. It was positive, now it's negative, so yeah, that doesn't support you, Jesse. And yeah, there you go. Alright, for number 5, you can solve this one using vertical angles and alternate interior angles over and over and over again. So we know that x and y are parallel, those are good, so these are parallel to each other, and we have a transversal z, good. Always, sometimes, or never. These guys can be tricky. It's saying 1 and 4, the measures add up to 180. Well, 1 and 4, that makes a line, so yeah, that's always true. It's like a theorem, yo. 5 minus 7 is 0, so 5 minus 7. Well, since they're at the same angle, it's like saying if my angle is 70 degrees and I subtract 70 degrees, what am I going to get? Yeah, you're always going to get 0. So that's an always. Z and y are perpendicular. Z doesn't look like it's perpendicular to y, but it could be. What if I move this a little bit? I would say this is sometimes true. Almost never, but sometimes, because if I just move z so it looks like that, then it is perpendicular. In this instant, it doesn't look like it, but it doesn't say it's not, so it could be true sometimes. 2 is congruent to 8. So 2 is a small angle, 8 is a small angle. I mean, just because they're both small, I'm going to say it's always true, but I'll give you theorems to support that. 2 is vertical angles with 4. 4 and 6 are vertical angles. 4 and 6 are alternate interior angles, and 6 and 8 are vertical angles, therefore 2 is congruent to 8. I've proved it. Always true. Oh boy, this one is going to be a handful. 2 minus 3. So if I do this, let me get rid of all this nonsense so we can see what's going on. So I'm saying if I do 2 minus 3 and 1 minus 4, this one is super, super tricky. So that normally won't work. So if you think of this as small and big, big and small, you can even attach numbers to it if you want to make it really formal, or it's still not formal, but it makes more sense. If I do 2 minus 3, that's a small minus a big. That means this thing is going to be negative. And if I do 1 minus 4, that's going to be big minus small, which is a positive. That never happens except in the case where z and y are perpendicular. That is not small and big, it's 90 degrees minus 90 degrees and 90 degrees minus 90 degrees. 0 equals 0. This is a sometimes true, surprisingly. These types of questions on the benchmark, I think almost everyone gets them right, even if you haven't seen it before. I'm adding 2 in the x direction, I'm adding 3 in the y direction. If I'm subtracting in the x direction, that means I'm going left, but I'm adding, so I'm going right. So this says right 2, and this guy says go up 3. So the y direction is up and down, the x direction is left and right, positive is right, negative is left, positive for the y coordinate is up, negative is down. With that, you're good. So I'm going right 2, up 3. Translation, 2 units right, so it's not left, and then 3 units up. That says down there, so you're not correct either. Correct answer is C. Alright, so let's read this. So we have this point F on the coordinate grid, and we're going to reflect that across a line to create F prime. Doesn't tell us what line. And then points E, F, and F prime are connected to create a triangle. Okay. Doesn't tell us anything about where to reflect that, but we'll go with it. Carrie says that point E must be on the perpendicular bisector of line F, F prime. Yep, I agree with everything that she's saying. Okay, so enter the equation of a line across F which could be reflected. Okay, so let's do the easiest possible example. If I do, it might be kind of hard to see, but if I do a line through the x-axis and I reflect over that, I come down here, so that means my point is right here. If I count up 3, I count down 3, this is my point F prime. That's what it's saying. I'm reflecting across some line, and I have to choose that line. As long as you choose a line that's going through E, that seems to, any line through E should technically work. I could have gone like this line through E, and then I'll have a triangle like this. There's my triangle. I could have done, I don't know, a really wonky triangle down here. No, that wouldn't work. This triangle right here, I don't know, it would be somewhere down here. It would be hard angles, but any line through E, and I think you're in good shape. This one is probably the easiest one. So we have f prime. The equation of this line, a review from Algebra 1, if it goes through the y-axis once, then it's y equals whatever the y-coordinate is that you pass through once. I pass through the y-coordinate of 0. The equation y equals 0 is perfect. There's like a bunch of different equations I could have used. I could have used x equals 0. Yeah, anyway. Enter the equation of a line across which f could be reflected to show that Carl's claim is incorrect. Okay, so anything that doesn't touch E and you're good. It doesn't say the line has to go through E, does it? Yeah, so are you guys ready? There's a point up here. Now E is definitely not the perpendicular bisector, which again we haven't talked about, but here's my triangle. That is a horrible triangle, Mr. Sindel. There's my triangle. E is not halfway in between these 2 points. Halfway in between those 2 points would be somewhere on this line, and E is clearly not halfway in between f and f prime. So any line would work. So an equation that would make it incorrect, y equals, I don't know, 6. Sure, just do a line right there. That would make f prime come up here, f prime, and there's my perpendicular bisector line, and E is not on that line. On to number 9. All right, number 9. So this one is a much harder question than the one that looked similar to this. The main thing to know from this one is the difference between what it means to be similar and congruent. Congruent means you have the same length. That's it. Similar means you have the same proportion. So if I multiply, then I have the same proportion. So they're definitely going to be similar. If I just only added or only subtracted, they would be congruent, but they're definitely multiplying. So the figure and its image, by the way, figure is the original thing that I start with. Image is the word for the thing after you apply some effect. So the image is this one, here is the figure. They are obviously not the same length because this one is twice the length. They're not the same length unless the length was 0, which is a dumb question. They're not going to do that. So they're not congruent. They are similar. And is it going up or is it going to the right? What would you guys guess? If you guessed up, you got it correct because it's the y that's going +1. Y is up or down and positive is up. So correct answer here is A. After reading number 10, I kind of realized that number 9 I misled you. As long as you're multiplying the x and the y by the same amount, then you are similar. But this one is not multiplying the x by the same amount, so it's not similar. The best way that I can explain that is let's assume we're doing this transformation. So let's assume that we have a triangle, and I'm going to not do anything to the x-coordinate. It's going to stay in the x-coordinate. Let's assume this is 1. And we're going to multiply all the y-coordinates by 3. So instead of 1 times 3, this height of 1 is going to go up to a height of 3. So height of 3. Instead of a height of 1, it's going to come up to a height of 3. And I'm going to move that point in a second. It's a little bit off, I know. And instead of a height of 3, it's going to come up to a height of 9, because 3 times 3 is 9. So, come on now. So, do these look like they're the same shape but enlarged? Similar just means you either enlarged it or you shrunk it. It totally looks like a different shape because I didn't enlarge it by the same x and the same y. So, we want to say that they're neither similar nor congruent. So, it's not A, it's not B, and it has been stretched in the y direction. Y is vertical up and down, so correct answer here is D. All right, number 11 is another untangling of a proof. It's kind of our last hard question on here. So we have a CD, and it's a perpendicular bisector, so that's the main thing. So perpendicular means we have a 90-degree angle, and bisector means it cuts it into 2 even pieces. It cuts it in half. So just knowing that, we can label this, yes, these things are all true. That's what it gives us in the problem. So we need to find a statement that shows why AE, why this length and this length are the same. We're trying to prove that, trying to get there. Okay, so I'm going to start with A. EFA, so this angle right here and this angle right here are 90 degrees. So far, so good. This line checks out. And AF and BF are the same. AF and BF are the same. That's true. And I'm immediately jumping down to hypotenuse leg theorem, which again, since you haven't seen any of these before, you might be wondering what that is. It means you need to have a hypotenuse and a leg that are the same. Well, I have a leg and I have a right angle, but here's the hypotenuse. It's saying, oh yeah, I have the same hypotenuse. No, you're trying to prove that you have the same hypotenuse. You're not allowed to use a theorem to prove itself. Like, that's recursive. Since I don't have a hypotenuse, I can't use hypotenuse leg. No. All right, B. EFA and EFB. EFA, so it's this angle and this angle add up to 180 degrees. I agree. So AEB must be isosceles. Oh my god, no. That does not work. Okay, so I'll show you why. What if my diagram looked like this? Okay, I think we can all agree that this is not isosceles. But yet this angle and this angle still add up to 180 degrees. Just because those two add up to 180 degrees does not mean I have an isosceles triangle. No. EFA and EFB equals 90 degrees, and that's because they're perpendicular, and those angles are the same. Yes, if they're both 90 degrees, they are indeed the same. That's a lot of information, but good. Definition of midpoint, we talked about that up here. Reflexive property, EF and EF are the same. So far, so good. Side angle side. So that means I need a side and a side with a sandwich of an angle. So it's saying that if I come back up here, so it told us that these two sides are the same. It said that this side right here is the same, and it sandwiched the angle in between it. So yeah, you can use side angle side. You have a side, then an angle, then a side for both of the same triangles. So they are the same triangles. And yeah, so everything checks out. The correct answer is C. Let's take a look at why D does not work. So it's saying EFA and EFB add up to 180 degrees. Oh no, this is off to a bad start. It's again saying that this angle and this angle add up to 180 degrees. EAF, so saying this angle plus this angle equals 90. What? How do you know that's 90? What if your triangle looked like this? Let's do something ridiculous, like now these two angles add up to like 20 degrees. How'd you get 90? I have no idea. It's not D. Okay, correct answer C. And our final example, which transformation, we'll get to that. So we need to scale up by a factor of 2, because 2 times. So which of these says scale factor of 2? Oh, they all say scale factor of 2, and that doesn't really help us much. All of this stuff is the same, so ignore that, it's all the same. And then these are the things that are different. Ah, okay, so it's dilation through the point 1, 0 or through 0, 1. No, whenever you dilate by not the origin, the math becomes really kind of difficult, and I never really teach that. But the reason I don't teach it is because it's way more complicated than that. It's not C, it's not D. It has to go through the origin if it looks like that. So after it goes through the origin, then I'm going to do add 1. Is that going to be right 1 or is it going to be up 1? What is your guys' guess? If you said right 1, you got it correct because it's in the x coordinate. Whenever x is positive, it goes right. When y is positive, it goes up. And I have no adding on y, so the correct answer is A. And that concludes our entire winter benchmark practice. So by finishing this video, that means you've taken your notes, you know how to do the actual benchmark problems, more or less. I know that a lot of this we haven't learned. Thank you for watching.